Hey guys, welcome back. So 3.2 is talking about the derivatives of your logarithmic functions. So like with the exponential functions, we have two different rules. One with the special base e, which is a nice number in calculus. It's essentially derived from calculus, that's why we like it so much. And then a non-base e. So if we have f of x equals the ln of u, again, like the exponentials, u is a differentiable function of x. The derivative of this would be u prime over u. So the derivative over the original expression. Whereas if it's log base a of u, so it's not a base e, it's u prime over ln of a times u. So the ln of the base is still showing up for our non-ln functions, our log base 2s, log base 5s, things like that. So if we want to take the derivative of this expression right here, so we know it's going to be a fraction. The numerator is the derivative of the inside there, so it would be a 16x. And then the denominator is the original inside, 8x squared minus 3. And more often than not, that's really as far as you're going to be able to go. There's not a lot else we can do with that expression right there. Now, if it was a monomial denominator, we'd be able to, reduce this expression a little bit because 6 and 8 do go together, x and x squared do go together. But that 3 kind of leaves nothing for us. All right, so here's an example of a monomial, but with a log base 4. So we set up our derivative here. Again, we're dealing with the derivative of the inside there, so that's 7x cubed becomes 21x squared. We have ln of the base times the original inside of 7x cubed. So we can recognize that will reduce. The 21 over 7 becomes a 3. X squared over x cubed becomes an x. So I'm going to actually write this as x ln of 4. I'm going to put that in front of the ln. I don't want you accidentally thinking it's ln of 4x, like the x is combined with the 4. So I'm going to put it in front of it. That's also why I have that little dot there to kind of just show for the original one, ln of 4 times 7x cubed, that they're not joined together. All right, so that would be our derivative. Not quite sure what's going on with my pen right there, why it doesn't want to draw sometimes. That's interesting. All right. Now, again, like with the exponential, we can talk about this in the context of a product rule, quotient rule, and implicit. So here's our product rule right here. We're going to leave it in this product format. We don't want to distribute because if we do that, it will create multiple product rules in the same problem. So there's our first function. There's our second function. So our derivative, first function becomes just simply 12x squared. We leave the ln of 4x cubed alone. And then plus, we leave the 6x cubed minus 2 alone. The derivative of ln of 4x cubed, well, would be a 12x squared over 4x cubed, which I can reduce that, and I kind of need to reduce that. Just simply a 3 over x. All right, we're going to leave it in that format right there. There's really nothing that can be gained from distributing the 3 over x. Again, besides having it as a product right there, we just have our two separate terms. There's nothing the whole thing has in common. So there's no factoring going on. The exponentials had an e everywhere, so that's kind of why we talked about factoring, because it just made sense. Here, the ln disappears when we do the derivative. It doesn't it sticks around, so it's not to our benefit. So we're going to go ahead and just simply say that's our answer right there and not go any further. Reduce the fraction, yes, but beyond that, don't do anything else. So with our quotient rule, here we'll have to be careful because it will create a fraction within a fraction, so we are going to have to deal with that aspect of it. But either way, that's our low, ln of 2x cubed plus 3, d high, which would be 30x to the fourth, minus our high, 6x to the fifth minus 2, d low, which would be our 6x squared over 2x cubed plus 3, all over our ln of 2x cubed plus 3 squared. And again, because we're squaring our natural log, we are not able to apply different log properties allow us to move the exponent as a coefficient, because that would be when we're squaring inside the natural log. Squaring the natural log expression, I can't do that. All right, so we do have a complex fraction scenario right here, so we should multiply everything by the 2x cubed plus 3 to get rid of that. So we would have an ln of 2x cubed plus 3 times our 30x to the fourth times then 2x cubed plus 3 minus our 6x to the fifth minus 2 times our 6x squared all over we'd have a 2x cubed plus 3 on the bottom as well, ln of 2x cubed plus 3, and again, the ln expression is being squared. Complex fractions are never really allowed, so we just simply multiply by that denominator to the entire thing to kind of get rid of that. There are some factoring that could occur. We can recognize that 30x to the fourth and 6x squared both have something in common. That's really as far as that can go, though. So it's not really to our benefit to, again, go further with the factoring. It's not going to do us any good here. It's a small little thing we can factor. Not really that helpful. So we're going to avoid factoring for this. And then finally, our implicits, the rules still apply. So we would have 21x squared plus a 2. 7 goes away. ln, this would become a 12y squared over 4y cubed, and then times dy dx. So we're going to go ahead and simplify that fraction. So we have 21x squared plus 2 would equal 3 over y times dy dx. So to get dy dx by itself, we got to multiply by the reciprocal, which is y over 3. So we would get dy dx equals, so this would be a 21x squared y plus 2y all over 3. All right, so implicit will still occur again with our natural log problems or log-based problems as well. And again, each one of those product, quotient, and everything rule, this implicit one was an ln. They could have easily been log-based 3s, log-based 4s, things like that. And we could have applied the same kind of rules. All right, so that's our exponential logs. So next up is our trig functions. We have 6 trig functions, so our 6 trig derivative rules. This is where it starts getting a little tedious with all the rules, because so far there hasn't been too much to memorize. Power rule is very straightforward. Even the product and quotient rule, as long as you're careful with the order, well, quotient rule, you're careful with the order. Product rule, as long as you're just careful to actually do 2 different pieces to it, you'll be fine. Chain rule is just the expression raised to a power, not that big of a deal. We're starting to add on more and more rules, and there's going to be more and more that you need to know. So a recommendation I generally have for my students, especially if they're prepping for like an AP calculus kind of class, is to have a separate sheet of paper somewhere where they're just writing out all the different rules for derivatives down as they go. So it's not part of the regular notes. It's kind of like off to the side, and they just kind of add to it as they go. Because by the end of the stuff with derivatives, so at the end of this unit, at the end of 4 and 5, which are all derivative type base units, you're going to have a lot of information. And having it all on one piece of paper is going to make your life significantly easier when it comes to studying for something like the AP test. And even if you're not prepping for an AP test, even if you're just prepping for just a regular calculus class, having all the derivatives in one place will make it a lot easier to prep for whatever test you got to do for that one. All right, so I'll see you next time with those trig derivatives.